Hello, welcome back. Professor Paul here, and this is my little Yorkie Max. And we're going to continue with our examination of the future value interest factor for an annuity. You'll recall that in the last lesson, we had defined the future value interest factor for an annuity as being equal to 1 plus r to the nth power less 1 all over r. And I showed you that that indeed did corroborate the individual cash flow type analysis. So this is good. This is the formula for the FVIFA. But then, of course, where did it come from is a very valid question. To really understand something, you need to know where the formulas you use came from. In other words, how are they derived? So let's derive this now. This comes from an area of mathematics known as finite series mathematics. And let's see how it works. Well, we start off by defining our FVIFA. And so the FVIFA is defined as 1 plus r to the 0 power, which of course is just 1, plus 1 plus r to the first power, plus 1 plus r squared, plus dot, 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 plus 1 plus r to the n minus 1 power. You'll remember when we had 3 cash flows in our annuity, we had an individual FVIF that had a value of 1, and the highest power to which 1 plus r was raised was 2. And so here we have a series of terms going with exponents ranging from 0 to n minus 1, and the implication, of course, is that we have n distinct terms in our series. So that's a definitional equation. Can't be wrong. We're defining FVIFA to be that. Now, a very...
If you ever want to see, like, not write for a second and talk to the camera, that one is recording still.
Okay.
So then I can switch back and forth.
Okay.
So yeah, just saying.
Thank you. Okay, so a very bright person, probably thousands of years ago, figured out how to work with these series. And what you do is you take your definitional equation, which I'll label equation 1, and you multiply both sides by a specific factor. And knowing the factor is important. In this case, the factor is 1 plus r. So I'm going to multiply both sides of Roman numeral equation 1 by 1 plus r, and in so doing, I'll get what I refer to as equation 2. So on the left-hand side of equation 2, we have 1 plus r times FVIFA, and that is equal to, well, now I'm going to raise every term over here on the right-hand side. Excuse me, I'm going to multiply every term on the right-hand side by 1 plus r. I'm going to have to distribute that individually. So the first term, 1 plus r to the 0 power, times 1 plus r to the first power. Well, this is 1. 1 times 1 plus r is 1 plus r. And this term, 1 plus r to the first power, multiplied by 1 plus r, will be 1 plus r squared. And this term, 1 plus r squared, multiplied by 1 plus r, would be 1 plus r cubed. Plus, dot, 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 plus, and then here we have our final term, 1 plus r to the n minus 1 power. Multiply that by 1 plus r, I'm going to get 1 plus r to the n power. Okay? So a very smart person a long time ago figured this was the first step. Now, once we have equation 1, our definitional equation, and equation 2, our modified equation, for which the equality is still true because we multiply both the left and right-hand side by the same factor, logic then is applied. We're simply going to apply logic. If the left-hand side of equation 1 equals the right-hand side of equation 1, and the left-hand side of equation 2 equals the right-hand side of equation 2, logic tells us that the difference in the left-hand sides must equal the difference in the right-hand sides. So on the left-hand side, we've got, and I'll do equation 2 minus equation 1, 1 plus r times FVIFA minus the left-hand side of equation 1, FVIFA. And then I'll subtract the right-hand side of equation 2. I'll subtract from the right-hand side of equation 2, the right-hand side of equation 1? Well, I'll cancel where the canceling can occur. I'll do this in black. This cancels with this. 1 plus r squared cancels with 1 plus r squared. I think you'd agree that this 1 plus r cubed would be the next term in the series. And I think you'd agree that this 1 plus r to the n minus 1 will be the term that precedes this term. Okay? And what's important to see here is that when we do 2 minus 1 on the right-hand side, we are left with two terms. In blue, we're left with this term, and we're left with this term. Don't forget, this term is the same as the number 1. Okay? So we're going to be left on the right-hand side with 1 plus r to the nth power minus 1. Okay? So let's just work the algebra with the left-hand side. We'll distribute the FVIFA over 1 plus r, so we have FVIFA plus r times FVIFA minus FVIFA is equal to 1 plus r to the nth power minus 1. Now, here we have FVIFA minus FVIFA, so on the left-hand side we have r times FVIFA. On the right-hand side we have 1 plus r raised to the nth power less 1. And then, therefore, dividing both sides by r, we have FVIFA, future value interest factor for an annuity, equals 1 plus r to the nth power less 1, all divided by r. So there we've proved that, yes, indeed, this is the appropriate computational formula for our future value interest factor for an annuity. That's FVIFA. Now, an application of this. Let's say we were going to deposit some money into an account beginning at some date 3 periods from now, date 3, and then at date 4, then at date 5, and then at date 6. Okay? So we're at date 0, there's also a date 1 and a date 2, but we're going to do some, we're going to make some deposits at dates 3, 4, 5, and 6. Let's just pretend $1 million. 1M. Okay? So there, that's an annuity. Equal size cash flows, a finite number of them, here are 4, and the interval between payments is fixed. That no payment is skipped. The interval here just happens to be 1 period. So, what is the balance that we'd expect to have in the account if we indeed made these deposits at each of these dates as of date 6? Well, again, I could take and look at each individual deposit separately and move this deposit forward 3 periods using its own FVIF. But now that we have our tool, the future value interest factor for an annuity, let's apply that. And now we'll see that the application formula for the FVIFA looks like this. So again, this is the application formula for FVIFA. And this is future value of an annuity measured in dollars is equal to annuity cash flow, also measured in dollars, multiplied by the future value interest factor for an annuity. And here I'll just put within the parentheses R and N, reminding you that every FVIFA is a function of the value of 2 variables, R and N. There's an infinite number of FVIFAs because there's no restriction on the values for R or N. Okay, so in this example, the value of R I'll stick with R being 0.1 just because it's convenient to work with, and I've memorized some of the 1 plus 0.1 raised to a power values, makes things easier. And the value of N here will be 4 because there are 4 cash flows in the annuity. Remember, the fact that the annuity is making payments at dates other than 0, 1, 2, etc. does not matter at all. The way we built our future value interest factor for an annuity left us with an operating rule, that being N is the number of cash flows in the annuity, no matter when the cash flows occur, provided the cash flow stream qualifies as an annuity. Again, equal size cash flows, a finite number of those cash flows, and none of them are skipped. Okay, so in this example, the annuity cash flow value is $1 million. And the FVIFA is going to be 1 plus R, or 1.1, to the nth power, N being the number of cash flows in the annuity 4, minus 1 all over 0.1. Okay, that dot right there means multiply by. And so right here is the future value of the annuity, 1 million times this value right here. And now we have the value of this at 4.641 multiplied by 1 million. And of course that is equal to $4,641,000. That's the future value of the annuity. Now in this case, it's a date 6 value. Very important that you understand something. Whenever we use an FVIFA, it will always, repeat, always, give us the value of the annuity as of the precise date of the last cash flow of the annuity, whenever that might be. In this case, we have a 4-period annuity with the last cash flow at date 6. And one has to remember that we've built this FVIFA such that it will always give us the value as of the date of the last cash flow. Remember, one of the terms in the sequence when we looked at the individual FVIFs, which in sequential order had a sum equal to the FVIFA's value, one of those terms was a 1. Well, that one FVIF term is associated with the very last cash flow. And so therein is a proof, if you will, of the fact that the FVIFA will always give us the value of our annuity as of the date of the last cash flow. And this example here shows us that a 4-period annuity need not end at date 3 if it begins at date 0, or at date 4 if it begins at date 1. It can begin and end anywhere. It's crucial to understand that. Specifically, we'll be glad we understand that when we work through some of the problems later on. So, a few words about annuities. If I put some dates up here, 0, 1, 2, 3, 4, 5, 6, 7. I'm just going to show you using different letters to represent the, for example, right here, X, X, X is an annuity, occurring at dates, with the cash flows occurring at dates 0, 1, and 2. Also, Y would be an annuity. 2 payments is fine. Also, Z, paying at dates 1, 2, and 3 is an annuity. But also here, beginning at date 1, Q, and then at date 3, Q, and then at date 5, Q, and then at date 7, Q. That also is an annuity. We have a finite number, 4, of equal size, Q, cash flows for which the interval between the cash flows is constant. In this case, it's 2 periods. Don't be confused by the fact that, for example, if these numbers here are years, and you see perhaps an X in every one of these, and you might think, well, then this down here with the Q's, every other one couldn't possibly be an annuity. That's incorrect. And the way to see it is just, if these are indeed years, we could translate this annuity into months, in which case you would have an X and then 11 blanks, then another X, and 11 blanks, and another X. And those 11 blanks would just be reflective of the fact that you were translating yearly periods to monthly periods. Okay? So know and be comfortable with the fact that the characteristic for an annuity that involves the interval between payments be a constant is perfectly appropriate. Now, one thing that's interesting is we make a big deal about the interval between payments and annuities being fixed, but if you really think about it, and I encourage you not to think too much about it, months aren't the same number of days. So if you were to extend that, go from years to months and months to days, you would find, I guess, a problem in that months have a different number of days. But you needn't be concerned with that now. There are ways of dealing with that. We just theoretically consider a month to be a month. And that is the end of my little discussion here of our third interest factor, future value interest factor for an annuity, and its application formula, one more time, is right here within the red rectangle. Future value for an annuity is equal to annuity cash flow times the FVIFA. Some review to this point. Whenever we use an FVIFA, the interpretation or the meaning of N associated with the FVIFA is the number of cash flows in the annuity. Also, whenever we use an FVIFA, it will always give us the value of our annuity as of the precise date of the last cash flow in the annuity. And that's all I have for now. Don't forget to subscribe. Thanks for watching, and don't forget to click on the like.